last lecture, I had spoken in some detail about the third postulate of quantum mechanics, which pertain to measurement, basically expectation values and eigenvalues of operators which represented observables. We spoke about measurement outcomes, repeated measurements, and how exactly expectation values are obtained and related to measurement outcomes in an experiment. Now, in this context, a very important question arises: how well can you make simultaneous measurements of two observables? You can always make simultaneous measurements of observables. Question is, can you measure both of them simultaneously to arbitrarily high precision? And this is really the content of the uncertainty principle, primarily due to Heisenberg, and it is the uncertainty principle that I will discuss in some detail today. So, the topic today is the uncertainty principle. The history of the uncertainty principle is rather interesting. Dirac and Jordan had proposed the transformation theory. The transformation theory by Dirac and Jordan was really based on the theory of linear vector spaces, and the theory helps one understand both wave mechanics due to Schrödinger primarily, and matrix mechanics primarily due to Heisenberg within the mathematical structure of linear vector spaces. This was due to Dirac and Jordan. Now, Heisenberg, in an attempt to understand transformation theory, had a glimpse of the uncertainty relation in the following sense. He realized that it was not possible to simultaneously measure to arbitrarily high level of precision certain observables. For instance, the position of an object along with the corresponding linear momentum cannot be simultaneously measured to an arbitrarily high level of precision. So, he constructed a Gedanken experiment, a thought experiment, to prove this point. Now, the thought experiment was all about a gamma ray electron microscope, where the gamma rays interacted with the electrons, except that the experiment as conceived by Heisenberg assumed that the interaction was like collisions between mechanical objects, which is not quite the truth. However, although the experiment itself as conceived in its original form by Heisenberg is not precise, the outcome of the experiment is certainly true, and it is really to be attributed to Heisenberg. The fact that simultaneous observation in quantum mechanics is very different from simultaneous observation of two variables in classical physics. So, it was in 1927 that Heisenberg suggested this, that there was this relation between position and linear momentum and so on. But in 1927 later, Kennard actually produced a very precise mathematical expression for this uncertainty relation. The Kennard relation starts off from the fact that x and px, position and the corresponding linear momentum, do not commute with each other. I had spoken about this towards the end of my last lecture, and just using the fact that this is the commutation relation between x and px. Kennard showed that the variance in x, if the variance in x is delta x squared, and the variance in px is delta px squared, where the variance of course is defined as the expectation value of x minus the average value of x, the whole squared, and so on. So this can be easily checked to be expectation value of x squared, that is the first term, minus expectation value of x, the whole squared. So this is the variance. Similarly, I can give a definition for p sub x. What Kennard showed was that delta x, delta px was greater than or equal to h cross by 2. This is a very interesting statement, because however good the experimental measurements may be, however good the instruments may be, there is always a minimum uncertainty, delta x, delta px equal to h cross by 2 in some state, which is a minimum uncertainty state, and for other states it is greater than this minimum value. In 1929, Robertson derived this uncertainty relation in a more general setting, where two operators A and B were considered Hermitian operators because they represent observables, and Robertson showed that delta A, delta B was greater than or equal to half the modulus of the expectation value of the commutator of A with B. It is pretty clear that if A and B commuted with each other, then this quantity became 0, and you have delta A, delta B greater than or equal to 0. But in general, this is true. In 1930, Schrödinger generalized it to give his uncertainty principle, which can be stated in this fashion. Certainly the first term is present, and then there is an addition which involves the anti-commutator of A minus expectation value of A with B minus expectation value of B. The anti-commutator is defined between two operators A and B as AB plus BA. Sometimes one uses the notation AB plus for the anti-commutator and just AB for the commutator, the square bracket AB for the commutator and AB with a plus out there for the anti-commutator. So you see there are two terms that contributed to delta A squared, delta B squared. These are the variances in A and B in this particular state. So it is clearly a state dependent statement, and in a given state the product of these variances is greater than or equal to this contribution, one from the commutator and the other from this anti-commutator. So since these are all positive quantities, it is pretty clear that delta A squared, delta B squared is definitely greater than the first term, and that is why you get the relation which Robertson gave. So this is due to Schrödinger. This is Schrödinger's uncertainty principle. In order to derive this uncertainty principle and study the various ramifications of the principle, one really starts with the Schwarz inequality. So I will first derive the Schwarz inequality and then proceed to explain the uncertainty principle in this context. So, Schwarz inequality is merely this statement. Suppose you have two states, psi and phi. Norm of psi times norm of phi is greater than or equal to the modulus of the inner product of psi with phi. It is clear that if phi were the null vector or if psi were the null vector, then the equality holds, because this side is 0 and so is this side. But in general, the non-trivial statement would pertain therefore to vectors which are not null vectors. Let me recall that the norm is the positive square root of the inner product of psi with psi. It is the length of the vector. It is a generalization of the modulus or the length of a a vector in usual three-dimensional space. So, let me first consider this object, ket psi plus a phi, where a is some constant, a complex constant. Now, clearly the bra is this. These are states in the linear vector space. I wish to find the inner product of psi plus a star phi with psi plus a phi. Now, this object is clearly the inner product of a state with itself, and therefore is greater than or equal to 0, and since these are not null vectors psi and phi, it is greater than 0. In any case, this object in general is greater than or equal to 0. But I can expand this, and I therefore have the following. If I did a term by term expansion, this quantity is greater than or equal to 0. A is an arbitrary constant, and therefore I choose a specific A. Let me choose A to be this object minus phi psi by the inner product phi phi. So, all I have to do is substitute for A and A star. It is clear that A star is minus of psi phi divided by phi phi. So, once I substitute, I have psi plus a star phi, or anyway that is greater than 0. 0 is less than or equal to psi psi, substitute for A, this object is in general a complex number, and this is its complex conjugate. So, that is like z, z star. The third term is the same as the second term, because these are numbers and therefore they can be commuted across. Then I have another term, modulus of A squared, which is A star, that multiplies phi phi. So, I can score that out, and now I multiply throughout by this inner product. That is from the first term. I am just clubbing the second and the third terms. and the third term is simply this, the same as the second term, half of the second term. And therefore, I have 0 is less than or equal to, this is norm psi squared multiplied by norm phi squared. Between these two, I just have minus psi phi with phi psi, and that is simply the modulus of psi with phi, the whole squared. I could have well written this as phi here and psi there. I should write this clearly, that is a psi. Okay. Therefore, taking it to the other side, I have got Schwarz inequality. Therefore, norm psi norm phi is greater than or equal to modulus of the inner product of psi with phi, and that is Schwarz inequality. So, this is something we use in order to derive the uncertainty principle, which is what I will attempt to do now. For this purpose, I consider two operators A and B, Hermitian operators representing observables. I look at the state A minus expectation value of A acting on psi. If I want to find the variance, that is the expectation value of A minus expectation value of A the whole squared. So, I can well write this as psi, and this is Hermitian. So, this is what it is. I could call this object psi 1 just for notation, and therefore, this is psi 1 inner product, which is norm of psi 1 the whole squared. Similarly, I can construct a state psi 2. So, delta B squared is obtained in the same manner as I did delta A squared, and that is psi 2 squared. The idea is to find out what is delta A squared, delta B squared. In other words, norm psi 1 squared, norm psi 2 squared. So, this is like psi 1 and that is like psi 2, and therefore, I use the Schwarz inequality right away. So, because of this, I know that norm psi 1 squared, norm psi 2 squared is greater than or equal to the modulus of the inner product of psi 1 with psi 2 the whole squared. This is a complex number. It has a real part and an imaginary part. So, the real part of this complex number is this, and the imaginary part so, this complex number can be written in terms of its real part and its imaginary part. We want its modulus squared. The modulus squared is clearly going to be the real part squared plus the imaginary part squared. So, let me consider that. So, if I want the modulus squared, that is as good as saying has two parts. So, let me consider first the real part. When I expand it, it is simply half the inner product psi 1 psi 2 plus psi 2 psi 1. Plus B minus expectation value of B, A minus expectation value of A. You could put hats on all these objects to show that they are operators, but in this notation it should be pretty clear what the operators are. But this is simply half of anti-commutator of A minus expectation value of A with B minus expectation value of B. We are interested in the square of this, and therefore, this is quarter modulus of the expectation value of the anti-commutator of A minus expectation value of A with B minus expectation value of B squared, which is the structure that we see here. This term from the Schrodinger uncertainty relationship has already appeared. We have accounted for the anti-commutator. So, next thing is to look at the commutator, which is the imaginary part. In a similar manner, we can show this. Commutator of A with B, the expectation value of that mod square. So, this really comes from the imaginary part of an appropriate inner product, and this comes from the real part of the inner product. So, putting the two together, I get delta A squared delta B squared is greater than or equal to this term plus that term, and that is the proof of the Schrodinger uncertainty principle. Now, it is good to discuss certain cases in this setting. First of all, let us go back to the two-level atom model, and since the uncertainty relation involves commutators, it would be good to look at objects which do not commute. So, my first example would be the two-level atom, and just to remind you, S plus takes us from ket G to ket E, and S minus takes us from the excited state down to the ground state, and S plus is Sx plus Isy, and S minus is Sx minus Isy. I want to look at an eigenstate of Sz. So, we know that these two are the basis states which are eigenstates of Sz, and just to refresh your memory, these are the corresponding eigenvalue equations. We also have a commutator algebra in terms of S plus, S minus and Sz. They look like this. So, I am interested in finding out delta Sx squared delta Sy squared, the product of the variances in Sx and Sy, and the state that I consider is an eigenstate of Sz, say ket E. So, I use the uncertainty relationship. Now, the first term is the commutator. So, look at the left hand side of the uncertainty relationship. First of all, the commutator of A with B in this case is the commutator of Sx with Sy, which is IH cross Sz. I want to find the expectation value of the commutator of Sx with Sy in the state E and take the mod square of that expectation value. That is the same as modulus. I pulled out the IH cross. SZE gives me, I can forget the I because I am taking the modulus. So, that gives me an H cross, the SZ gives me another H cross by 2, and this is to be squared. So, I basically have H cross to the power of 4 out there, and there is an H cross by 2 here, and therefore, I have H cross to the 4 by 4. So, this is what I have. So, this is the contribution from the first term. So, delta Sx squared, delta Sy squared is greater than or equal to quarter of this plus X cross. Now, this comes from the anti-commutator. This is the contribution from the anti-commutator of Sx with Sy. So, let us find out what that is. I wish to find out the expectation value of Sx minus expectation value Sx in the same state E, the anti-commutator of that with Sy minus expectation value of Sy in that state, and then of course the mod square and so on. First of all, in the state E, the mean value of Sx is 0. The simplest way of seeing this is to write Sx as S plus plus S minus, and since S plus acts on E to destroy it, there is no contribution from that term, and S minus acts on E to give me G, ket G, and ket E and ket G are orthogonal to each other, therefore, there is no contribution. Similarly, this average value is also 0. So, these terms drop out, and all I have is to find out the modulus of the anti-commutator its average value and square it. I need to estimate what is Sx Sy plus Sy Sx. Now, apart from factors, numbers which I can pull out, this quantity is S plus plus S minus, S plus minus S minus, plus S plus minus S minus with S plus plus S minus. So, the first term is an S plus squared which doubles up. So, I have a 2 S plus squared, but when S plus acts on E, it destroys it, and therefore, there is no contribution from there. Similarly, there is a minus S minus squared, and that comes twice over, but again there is no contribution from that, because S minus acting on E twice, first time gets it down to G and the next time destroys it. Then there are cross terms. There is an S minus S plus S minus, and that cancels out. Then there is an S plus S minus with a negative sign, and that cancels out with a term here, and therefore, this contribution is 0. Thus, it turns out that the anti-commutator does not contribute at all, and any contribution that comes to the right hand side of the uncertainty relation is from the commutator. And so, I have delta Sx delta Sy is greater than or equal to H cross squared by 4. So, here is an example where I have objects that do not commute with each other, and therefore, I have a minimum uncertainty value of h cross squared by 4. This happens in the state E, which is an eigenstate of Sz. You can construct states where it is greater, where this uncertainty product is greater than h cross squared by 4. It would be a good exercise to see what is the value of this product delta Sx, delta Sy in the other basis state ket G, as also in superpositions of ket E and ket G. Now, let me look at another example. My next example is to find out, again in this two-level model, the uncertainty product delta Sx, delta Sz in the eigenstate of Sz, that is ket E. So, what is it that I have here? This is an eigenstate of Sz, therefore, delta Sz is equal to 0, and therefore, delta Sx, delta Sz is equal to 0. But that does not mean that delta Sx is 0 in the state ket E. This is in fact finite, and we can check this out. So, what is the variance of Sx in this state? So, delta Sx squared in the state ket E is the expectation value of Sx squared minus expectation Sx the whole square. This is 0 as we have seen earlier, but this object is not 0. There is a spread in the measurement of Sx. We can compute that right away. Therefore, Sx squared is quarter S plus plus S minus times S plus plus S minus. Now, it is clear that when these operators are sandwiched in the following manner, between the states ket E and bra E, this does not contribute and this does not contribute. So, the contributions are 0 from here, but this does, because S plus S minus out here, S minus acting on E gives me G, and S plus acting on G takes it back to E, and there is an E on this side. Similarly, here I have an S plus acting on E which will annihilate and therefore not make a contribution, but I do have this term which stays. So, essentially this is quarter expectation E S plus S minus E, and S minus E takes it to G, but S plus takes it back to E. So, apart from a number which is non-zero, there is a non-zero value for expectation Sx squared, and therefore, delta Sx the whole squared is not equal to 0, although the mean value of Sx in the state ket E is equal to 0. The following points emerge. We have an uncertainty product of this kind, that if you make a measurement of observables A and B, look at their average value, their variances and so on, then the product of the variances satisfies this relation. There is an inequality here, could become equal for some states. We have seen the following cases. If delta A delta B product is greater than 0, then clearly the contribution has come because this or these two are non-zero. It is clear therefore that delta A is not equal to 0 and delta B is not equal to 0. So, this was the first example we had. Example, A was Sx and B was Sy, and the state considered was ket E, which was an eigenstate of Sz. Suppose delta A delta B is equal to 0, which is what we had in the second example. A was Sx and B was Sz, so delta Sz was equal to 0, the state considered was ket E. It does not mean, it does not imply that delta A is 0 and delta B is 0. It does not imply this at all. It simply means that one of them is 0 in general, and that is what we have seen in this example. Now, it is possible that delta A delta B greater than 0 equal to a finite quantity and AB commutator is not equal to 0, and that is how the contribution came. It is possible to make delta B 0, which means you measure B with infinite precision. In that case, the spread in A is going to be very large, such that the product of 0 and infinity gives me a finite quantity. So, it is possible to be in an eigenstate of B such that there is infinite precision in the measurement of B, but then you have really very little idea about the actual value of A when you measure it in that state. So, I look at another example right now, and that has to do with the position momentum uncertainty relation, which is what Heisenberg gave us and Robertson formulated precisely. In that case, looking at the general uncertainty relationship, I have variance delta x squared delta px squared is greater than or equal to quarter of the modulus of the expectation value in the state considered of the commutator of x with px whole squared plus quarter of the anti-commutator's expectation value, the anti-commutator being x minus expectation value of x with px minus expectation value of px in that state. Now, if you look at this, x px is IH cross identity, and therefore, delta x squared delta px squared is greater than or equal to quarter h cross squared, telling us definitely greater than this, because this could also contribute perhaps. So, delta x delta px is greater than or equal to h cross by 2. The minimum uncertainty state is 1, corresponding to which delta x delta px is equal to h cross by 2. And we will see that the ground state of the oscillator, for instance, is a minimum uncertainty state. In optics, the 0 photon state is a minimum uncertainty state, and so on. Minimum uncertainty in these variables. In order to actually make this estimation and give an example, a concrete example, I have to consider a specific system, and it would be good right now to move on to a slightly more complicated system, a system which does not have two discrete levels as its eigenspectrum for the Hamiltonian, but an infinite number of discrete levels for the eigenspectrum. In other words, it would be good to take an example which pertains to an infinite dimensional linear vector space, a discrete infinity of levels. The simplest thing that one can consider is a multi-level system where the eigenvectors are equally spaced, and indeed this is the situation with the harmonic oscillator. So, it is a good thing now to consider the next level of complexity, which is an infinite dimensional linear vector space, but with a discrete equally spaced energy eigenspectrum. So, if you consider the simple harmonic oscillator and quantize it, before we actually proceed to do the problem, solve the problem explicitly, we take cognizance of the following. The classical Hamiltonian, assuming that the oscillator is in along the x axis, is px squared by 2m, oscillator of mass m, plus half m omega squared x squared. I am going to drop the suffix x simply because there is no other momentum in consideration. In terms of operators, that would be p squared by 2m. In quantum physics, this is h classical. H quantum is an operator plus half m omega squared x squared. We will see that there are an infinite number of energy levels for this Hamiltonian when you quantize the system. The ground state of this system happens to be a minimum uncertainty state in x and px, and if you wish to give a position representation to the ground state, it will turn out to be a Gaussian in x as also a Gaussian in p, simply because I will establish shortly in the course of the following lectures that the position space and the momentum space are Fourier transforms of each other, and therefore Fourier transform of a Gaussian being a Gaussian, when you go to the momentum space, the structure of the wave function, the form of the wave function as a function of momentum does not change. So, the Gaussian turns out to be a minimum uncertainty state. Now, x and p happen to be infinite dimensional matrices. I could construct operators out of these which would take me from one energy eigenstate of the oscillator to the next energy eigenstate of the oscillator, and these operators are going to be analogues of s plus and s minus in the spin system, with of course the important difference that there is an infinite set of energy levels in the case of the oscillator, as we will set out to prove shortly. Suppose we forget all the constants here and I consider a generic system where I have set, for convenience, I set m equal to 1, omega equal to 1, h cross equal to 1, and so on. If I did that, well, there are only these three in this context, then my Hamiltonian, the quantum Hamiltonian, is simply x squared plus p squared by 2. I will put back the m and the omega and the h cross later, with the commutation relation that xp is equal to I times the identity operator. I could find combinations. I could find a combination A, which is x plus IP, and A dagger, which is x minus IP. and obtain the commutator of A with a dagger, I could represent this algebra in terms of the commutator between A and A dagger. Now, first of all, let us find out what is A dagger A. It is clear that A and A dagger are individually not Hermitian operators. So, A dagger A is x plus I p, x minus I p times x plus I p, that is x squared minus p x plus minus I p x plus I x p plus p squared, which is the same as x squared plus p squared plus I commutator of x with p, which is x squared plus p squared, and x p is I h cross. I have set h cross equal to 1. So, that is x squared plus p squared minus 1. Therefore, the Hamiltonian, the quantum Hamiltonian, can be written as A dagger A plus 1 by 2. If you wish, it is easy to absorb a root 2 in A and A dagger, so that A dagger A already has a half here. So, in standard notation, this is what we do. Multiply the whole thing by a half, so that the quantum Hamiltonian can be written as A dagger A plus half. But it is a Hamiltonian, and if you put in the h cross, the m and the omega properly, you actually land up with the oscillator Hamiltonian to be A dagger A plus half h cross omega. That has got the dimensions of energy in any case. One could study the quantum oscillator using the Hamiltonian A dagger A plus half h cross omega. I would formally define it properly in terms of x and p, putting in the h cross, the m and the omega in the suitable places. But the algebra xp is equal to I h cross is equivalent to the statement that A dagger commutator, given that xp is equal to I h cross. In this case, I am writing I because h cross is equal to 1. The commutator of A with A dagger is the commutator of x plus I p with x minus I p. I have the commutator of x with minus I p, and that gives me an I h cross out there. Then I have the commutator of p with x, which is minus I h cross. But I have set h cross equal to 1, and therefore, I am going to get rid of that. Thus giving me 1 here. Instead of writing xp is equal to I could have well written the commutator of A with A dagger is equal to 1. So, these are equivalent ways of writing the algebra of the commutators. Even as we wrote in the spin system, the commutation relation Sx Sy commutator is I h cross Sz cyclic, or equivalently in terms of S plus S minus commutator, I could work with xp is equal to I or with A dagger is equal to 1. My next lecture, I will use this Hamiltonian A dagger A plus half h cross omega for the quantum oscillator Hamiltonian, and show what exactly is the minimum uncertainty state in the case of the oscillator. The equality, the Heisenberg relation equality delta x delta p is equal to h cross by 2 would be established for the ground state of the oscillator.